Okay.
I have a question for Yoshio. Some of the line ratios that you show has one optical line as well. I think that at least 2 ratios that you show. So how are you combining the virtual data, and from where are you taking the optical data, and how is the difference of spatial resolution going to interfere in the ratio?
Right, so the optical data that went into what I presented today was all obtained from wherever archive that we can find, and then we always try to get the optical line strength from exactly the same location of the fine grained data that we have. So we are very careful about the spatial correlation. So for that one, the spatial correlation is good.
But then are you taking a constant value for the optical line? So you're taking a position in the nebula, and then you're taking a constant value for the optical line, and then applying that.
No. So we basically section the optical image into the pixel resolution of the partial data, and then get the optical data out of that section. So the spatial resolution is reduced to the partial level, and then conversion to message.
For Soviet?
Question for Devika. How many of your so-called post-AGB stars you estimate to be post-RGB stars? Because the more you take out of our true post-AGB sample, the fewer there will be, and the relatively shorter the time scales that are implied for their lives will be. So suddenly this will change the picture of this reaccretion idea that that the post-AGB stars go through, and that causes them to stall in their evolution. If you take most of them away and say they're post-RGB, they're different objects, then we have to change our idea of these Van-Winkel objects.
Okay, so we found almost equal populations, but from what we find more post-RGBs than post-AGBs, so about 55 or 50%. But it's mostly equal, and the only thing that separates them is their luminosities. So I don't know if that is, I suspect that there's no observational bias in that, because we take stars all the way from 500 Elson up to 35,000 Elson, and then we put it on the HI. But yeah, so it's probably half and half. But it's more likely to see more post-RGBs in the sense that they stay longer because they have longer evolutionary rates in their recreating stuff. On the post-AGB, they do them with their disk sources. So what I can tell you is we definitely see more disk sources than shells, which we think come from single stars because does that answer your question?
Yeah, so you're taking about half, if this holds for the galaxy, you're taking about half of our populations out.
Yes,
It transforms into a different deduced lifetime for the post-AGB objects.
Well, in the SMC, I don't have full numbers, but in the SMC, there's more post-RGBs than post-AGBs, but like the numbers are just border, they're about the same really at the end.
Don't you have a velocity bias there?
Just this
Don't you have a velocity bias because you have an upper limit cut off, and that would affect more the AGB threshold?
But that's 35,000, and we don't think that post-AGB stars are more luminous than 35,000 Elson, because they become then supergiants. Because if you plot them on the HI diagram, they're way far because they have higher temperatures. So they're more of the So we put in that luminosity cut on purpose because we want to really,
By the way, I wouldn't say that the shell-like objects come from single stars.
Yeah.
We don't know.
Yeah, we don't know. Likely, or maybe. They could be post-AGB stars with really compact orbital periods, but we don't see them. You know what I mean? They could be binaries with really compact orbits, but
everybody here believes that aspherical planetary nebula pre-planetary nebula come from binary stars. So if these shell-like objects, we don't have their morphologies, if they have morphologies like the the binary evolution than the objects which you're talking about, which are disprominent objects in my lecture. Yes, the question. Yeah.
From your experience on large machine learning and small machine learning, could you give us a recipe how to recognize post-RGB or post-RGB in our class? How to recognize post-RGB and post-AGB in our galaxy? I'm asking about experience about from LMC and SMC, and if it is possible somehow to distinguish between these two sources if we have no idea about the distance.
So once data comes out with luminosities, that's the only way, because we use luminosities to tell them apart. So we find when we plot our stars in the ETA diagram, they evolve off the RGB. So you need to know luminosities to be able to tell them apart. So once Gaia comes, you probably be able to tell it.
Thanks. I have a question for Margarita. You have these two groups of, let's say, world planetary nebulae, and you separated in those with no nitrogen 2 sulfur 2 and the other. I think your samples are biased. I think those that don't have the low ionization shape, no nitrogen 2, no sulfur 2, are very low mass planetary nebulae, and the others are higher mass. Just put some.
You mean that the mature PNE belongs to...
Yeah, you call mature those without nitrogen and sulfur and the low ionization species, and the others are the one that I don't remember exactly the name.
What you're saying is that we have different masses for the two groups.
I think there are different masses because I think those without the outer shell, ionization outer shell, are optically thin and interesting.
I'm not sure because we have actually in the evolved, the highly evolved objects, we see. Well, I present to you the examples, typical examples. But in example, we have objects that have low solar brightness, but it seems that in some part of the image they have bright, it seems that in every stages it may be bipolar or something like that. Not all the objects in the sample are perfectly spherical objects. And I think that if we thought that the higher masses produce bipolar structure and something like that, we have a mixing in the two groups. But we perform non-parametrical tests to study the probability to get the sample in the same parent population, and we have found less than 1% that we got the samples from the same parent population. I don't think that we have those bias.
All right. Anything? Oh, Valentine, you've been waiting for a while. Go ahead.
Tosia is in the nebula you have shown. There is a strong change in the dust-to-gas mass ratio between different parts of the nebula, right? Yes. That obviously that can be a result. The question is, I think you estimated the gas mass from atomic lines, right?
Well, the way I did was that we looked at the ionized region, and then we calculate the ionized gas mass. And then we have to scale that to incorporate neutral and then also molecular. And then once we get the correct, spatially correct type of optical line data from the neutral, then we can estimate the neutral gas mass. And then once we get the CO mass right, then we can get the molecular gas portion.
So to estimate the molecular part,
from the
you
spider,
take your
but we haven't done that yet. So the numbers that I showed today were just calculated from the ionized portion and then scaled to include both neutral and then molecular. So the calculation, the estimation was not done individual. So that's something we need to work on still.
May I also ask to the Nika a question? Yes, in your studies, you first identified post-AGB stars, say, protoplanetary nebulae from the far infrared intensity, right?
Can you repeat that again? Can you repeat that?
Yes, okay, in your studies, you identify possible post-AGB stars first from the far infrared intensity, and
yes.
later you select optically bright sources to study the spectrum,
Yes.
right? My question is, which is the percentage between the optically bright and the total possible protoplanetary nebulae after your research?
Yes, so I don't have the numbers on top of my head. I understand what you're asking me is how many enshrouded stars do you not study, right? Because they probably have V magnitudes less than 20 and you can't observe them. But I'll have to check that because I did the candidate cut and I didn't go back to checking how many we don't take in. But it's a hard number to tell you because, I mean, there's about a million stars in the stage catalog, and then when you have a 24 micron criteria, you get about 200,000 or something. And then the stars that make it to be optically visible is about, say, 35 or 40,000 or something. And amongst them, how many are post-HB stars? I can't tell you because amongst the 200, the 1,200 that we selected, only 100 were post-HB stars. So, do you know what I mean? So, even if I make the cut in the optical, there's probably M stars and C stars and PNs, and so I can't. There's no way any of us can get that number unless we do all the stars and basically survey the whole SMC, which is a lot of work.
Well, I mean, that's not as, the situation not as bad as that because for the supposedly pre-planetary nebula in the LMC, which have, let's say, they're bipolar and they're less stores, so we're seeing that's when they can't see the star. There's, of course, a lot of work being done in the mid-infrared spitzer.
Yes.
So, you can get an idea of how many such stars are there. Looking at the spectrum, people have classified objects as post-AGB shell-like objects based on the mid-infrared spectrum spitzers.
Yes, but from the optical, then it's hard. Just using optical alone, it's hard to say.
Right, one has to combine to understand the number counts.
Absolutely.
My question was which percentage of sources were obscured by the nebula, so they are not identified in the optical and they were excluded from
But that
was my question.
but
But I understand how difficult it is to answer.
you started out with a sample where you selected.
There's always contaminants in the ones you do too. So the ones that are not optically visible, let's say 20,000 stars are not optically visible, but they all have a bit of an excess. But they can be M stars and 6 stars or whatever. I mean, maybe not M stars and 6 stars, but super AGB stars or YSOs that are enshrouded as well.
Yeah, so.
Just a question for Walter and Letizia as well. So I would like to make a statement and see if people agree or disagree. For as far as using planetary nebula as tools for the abundance gradient, we just don't care much about what we come up with in terms of evolutionary scenario, binary, non-binary, because what you're using is type 1, type 2, type 3. We kind of all agree that type 1s are more massive. The oxygen abundance probably not much processing, maybe there's a little bit, but it doesn't matter for the gradient. So it's kind of this problem, which is very important for galactic buildup, is kind of disassociated a little bit from the evolution and the issues we're having here in shaping and so on. Do you agree with this?
Just one short comment. In principle, I agree. The only difference that it could make if you have binaries, so you don't know exactly the mass. So that may have an influence on the interpretation of it because of the mass.
So I thank you for this question because this was a long discussion I had with my collaborators the other day, the common envelope experts and the evolution expert. Basically, the common envelope history of a star, the planetary nebula, it doesn't affect the amount of tidal states of the main sequence. So the main sequence is what marked this kind of timing on the galactic plane. So no, it doesn't really matter. The only reason why I give this talk here is that I think it is important to select out binaries. Sorry, I apologize. Select out bipolars because of the difficulty to find distance. So I think that once we have Gaia distances, we can do bipolars and we can see the whole picture. So we will improve many more qualitative with this game.
Can I say something? This year?
So this type 1, 2, 3, these things from many years ago when you have only one spectra out of PM, and then you get one number and you get one abundance. But that's why we are trying to do the spatially resolved abundance profile. And then the radial profile can be translated into time profile, and then connect to the evolution. That's why we are going to this direction.
But do you think that there would be a difference if you think that might change the abundance classification?
It remains to be seen. So we have to
That would be very nice.
And then the sensitivity is not wide enough to see far enough.
Yeah, they're in the back.
I'm going to cheat on my 1 minute talk and I'll advertise my poster now because of that comment. It's exactly about finding abundance gradients from optical data. I think the main issue might be that you're just not getting good abundances. So if you're interested in that, talk to me a little bit. But mainly, the conclusion that I've gotten so far is that the way that the empirical abundance method works is good for ballpark numbers, but it's not good for detailed abundance analysis.
Regarding the oxygen planetaries, I don't think this is my issue, and all I want to do is to attract your attention to a paper by Rodriguez and Clara in 2011 showing that in the solar vicinities and without the problem of distances, they are found that the planetaries in our vicinity have larger oxygen abundance than the eastern regions in our vicinity by 0.2. That's oxygen abundance larger in planetary. That's a real problem for gradients and for planetaries, of course. Why they are producing that oxygen at the metallicity of our solar vicinity, not very low metallicity medium.
That's probably migration.
Could be migration, but it's affecting gradients terribly.
So it seems that we are running out of questions here and also running out of time. We still have a few minutes. Anybody have a last question here? No? Okay, then I declare this session closed.